Hi students, just 3 more examples for this week, and then lots more examples for you guys to try on your own. The first one is going to be an example of where the proof does not hold for n is greater than 0, n cubed is less than or equal to n squared. And then I should say for n is greater than 0 and n is an element of the integers, which means that 1 cubed is less than or equal to 1 squared. So there are times where we can start to use induction to kind of prove something is not true. And that should be intuitive, that a cube is not really less than or equal to a square. Usually it's greater than or equal to the square, or at least greater than. So we can say for p of 1, we can let n equal 1, and then I know that n cubed is equal to 1 cubed, which is equal to n squared, which is equal to 1 squared, which is equal to 1. So that shows it. It actually shows that 1 is less than or equal to 1, and that shows the p of 1 case. And then for p of k case, we assume that n equals k, which implies that k cubed is less than or equal to k squared. Now, this, if I can show the p of k plus 1, I've actually proven that n cubed is less than or equal to k cubed. So at some point, we expect that to break down, and it's interesting to see where that happens. For p of k plus 1, I'm going to assume that n is equal to k plus 1. And I'm going to evaluate and compare k plus 1 cubed to k plus 1 squared. K plus 1 cubed follows the binary expansion k cubed plus 3k squared plus 3k plus 1. And k plus 1 squared is k squared plus 2k plus 1. Well, if I examine each of the respective parts, and I kind of stick a plus 0 here, and I look at comparing this, I know that 1 is greater than or equal to 1. I know that, if I examine these, I know that 3k is greater than 2k for k is greater than 0, because we said k is positive. I know that 3k squared is greater than 2k squared whenever k squared is positive. And k squared is always positive, so that would always hold. And furthermore, I know that k cubed is greater than 0, because k is positive. So by the additive there's a property in algebra, the additive property of inequalities. I can add up all my left sides and say that I know that k cubed plus 3k squared plus 3k plus 1 is greater than k squared plus 2k plus 1. And since that is k plus 1 cubed is greater than k plus 1 squared, that is a contradiction from what I wanted originally. That's the opposite of what I was looking for. And that points to this symbol, which means contradiction. Which means that we've thus disproven the original contention. And in a sense, we've actually proven the opposite, that n squared is actually greater than or equal to, or n cubed is greater than or equal to n squared. Okay. Second example. This is a more simple example, but this kind of shows you how this works. For any n, we're going to say n plus 1 is less than n. So this is interesting because if I start with a p of k condition, I can say that for n equals k, assume k plus 1 is less than k. And then I can check the p of k plus 1 condition. For n is equal to k plus 1, I know that k plus 1, I'm going to start with what we had before, k plus 1 is less than k, but I'm going to add 1 to both sides. K plus 1 plus 1 is less than k plus 1. And if I group that differently, like this, then I have what I need for p of k plus 1. I'm showing that adding 1 is less than not. Oops. So that should prove it. So where do we go wrong? Well, the original condition, p of 1 doesn't hold. And this is interesting because many times on these proofs, they'll kind of treat p of 1 as trivial. They'll just leave it and not show it, assuming that it's so obvious you wouldn't have to show it. But P of 1 does not hold, because P of 1 would mean that 2 is less than 1. So since that part fails, then that's a contradiction, and that proof does not hold. Okay. Last example, just to do one more of one that does hold. For n is greater than or equal to 1, we have 2 plus 2 squared plus 2 cubed plus 2 to the 4th all the way to 2 to the n, and that's equal to 2 to the n plus 1 minus 2. This is a number theory result. That's kind of an interesting result. I can prove that for P of 1, which means that when n equals 1, then 2 is equal to 2 to the n plus 1 would be 2 squared minus 1. So that holds. P of k condition means that n is equal to k. So 2 plus 2 squared plus 2 cubed all the way to 2 to the k is equal to 2 to the k plus 1 minus 2. And if I'm trying to show that for P of k plus 1, where n is equal to k plus 1, I'd start with 2 plus 2 squared plus 2 cubed all the way to 2 to the k plus 2 to the k plus 1. And I can simply just kind of take this and substitute that with 2 to the k plus 1 minus 2, and then add another 2 to the k plus 1. Well, algebraically, these are now like terms, so I have 2 times 2 to the k plus 1 and minus 2, and that's the same as 2 to the first, and if I multiply with the same base, I add the exponents, 2 to the k plus 2 minus 2, and thus that is shown. See, short one.